This is PreCalculus 12, Chapter 1.5. We're going to be looking at modeling and solving problems with polynomial functions. Word problems generally require a good understanding of English. It also requires knowledge about secondary subjects like physics, economics, chemistry, business. And when we're working on word problems, we want to create meaningful variables. So looking at the question, since we're using polynomials, we only want one variable. And per, each, portion, divvy, group, partition, these usually mean divide. However, sometimes it could mean multiply. Times, magnify, these mean multiply. Is, will be, was, this means equal. More, and, plus, increase, sum, total, tally, they usually mean add. Less, decrease, reduce, take away, deduct, discount, usually means subtract. And a dictionary or thesaurus can help with interpreting some words. Many of our word problems rely on physics, so here are a few basic physics formulas. Distance is 1/2 acceleration times time squared, plus initial velocity times time, plus initial position. So 1/2 at squared plus vt plus d naught, our initial position. Average velocity is distance over time, so v equals d over t. Time is total distance divided by average speed. T is equal to d divided by v. And here are a few formulas from business. Average cost is total cost divided by number of units. You can also think of this as price. Revenue is number of units times the cost per unit. And profit or loss is equal to revenue minus cost. Finally, we want to look at the final question to determine what the variable should be, to ensure that we don't have any further calculations to get the answer. So here's an example. A piece of cardboard, 28 by 21 centimeters, is used to make a box with no lid. What height will maximize the volume? So that's one question. What height will make the volume 750 centimeters? And the question is asking for height. So that should be our variable. So the first thing you want to do is draw a picture, because that will help you figure out your other equations. Our cardboard is 28 centimeters and 21 centimeters. So we're going to cut out corners to make the box. We're cutting off the height. And then we fold the box. So this is our length. This is our width. So our length, we have 28 centimeters, and we're taking off an h and taking off another h. So this is 28 minus 2h. The width is 21 minus h and another h. So 21 minus 2h. So we have L equals 28 minus 2h. Width equals 21 minus 2h. And our volume is 28 minus 2h. We just substitute into this formula. Try to do things in the same order that they show up. That way you don't miss anything. And multiply by h. And so when we get our answer, we'll answer this question. If we were solving for length or width, we'd have to do this calculation to get our final answer. And when you're asked these questions, you can leave the volume formula or whatever formula in factored form. You'd only have to change it to standard form if the question is asking for that. Okay, let's graph this on a calculator to get our answer. Okay, so we need to enter our formula. 28 minus 2. We don't have h on the calculator, so we just use x. 21 minus 2x times x. Now we need to set the window. So we can get a rough estimate. We take this number and multiply by this number. So we'll just say it's 30 times 20, so that's 600. And I want to not make that go so far back. And graph. Okay, that goes up very high before it comes down. So 600 is not big enough. And we just play with these numbers until we get something reasonable on the screen. So I'm just going to go really big, and that'll give us it's probably too big, but our domain is h has to be greater than 0. Because if it's less than 0, we would have a negative height, and that doesn't make sense. If our domain went up to 11, this is 2 times 11, that's 22. 21 minus 22 gives us a negative width, so that's not right either. So our domain, 0 and 10.5. And we want to make some final adjustments so that we can see all the key features of the curve. Okay, to find the maximum, we just need to go second calc, 4 for maximum, and you need to be on the left side of the hill. So we're to the left of the maximum, and we need to be to the right of the maximum. That way we can find the answer. And we get h equals 3.96 centimeters. And what is the maximum volume? Volume is 1040.0 centimeters cubed. Now I made the domain bigger for this graph just to illustrate a point. Why is this not an answer? Well, it's because we just determined the domain. It's got to be less than 10.5, otherwise the width will be less than 0 and the length will be less than 0. Okay, so that answers the first question. Now, our second question, you always have to read the question, otherwise you miss something. What height will make the volume 750 centimeters? Okay, so we need to go back to our calculator and we need to add a second equation, 750, and graph. Okay, so we have an answer here and an answer here. And for this, you will go second calc and you'll go intersect. It's asking for the curve, the other curve, and your guess. And we get 1.75. And you can do the same thing for this one, and you get your answer here, 6.0. 0.66 centimeters. Okay, be careful with box problems. There's different setups. This one has a single sidewall and has no lid. So you could have problems with lids. You can have problems with double folds. This one is a single fold because we're folding right along here and right along there. You can have problems where you actually fold twice because they want a stronger side. Okay, let's look at another example. The school is raffling off an iPad worth $700. They know that they will sell 500 tickets if the price is $5. For each dollar they increase the price above $5, they will lose 10x squared, where x is the dollar increase. And they'll lose 10x squared tickets. Ticket prices must be in dollars. How many tickets sold? Okay, our variable is going to be P. Okay, unfortunately for this problem, it's hard to use tickets as your variable. Everything is described in price. So we need to actually calculate the price and the revenue, and then we'll calculate the number of tickets at the end. So we'll call the price P. So we have P times, and it's times the number of tickets. We know there's 500 tickets going to be sold at $5. But we're going to lose, it says lose, so let's subtract 10x. Well, x is the dollar increase over $5, so it's P minus 5. That's our expression to get the dollar increase. And then we square this because it's x squared. And that's our formula. So we need to graph this. So we have x, 500 minus 10, x minus 5 squared. And we need one more bracket. And we need to set the window. Our dollar increase is probably not going to go much higher than $10. So we'll go -1 to 10. We're going to sell no worse than 500 times 5 because we're going to sell 500 tickets for $5 if there's no change. So it's 2,500. So that's a starting point, and we'll see what it looks like. Okay, so it didn't quite catch that. So we need to make the window a little bit higher. So we'll say 5,000. You just have to guess and check sometimes. And I'm just going to make this a little bit bigger, 15. And graph. Okay, so we see the maximum here. And that looks like a good left bound. And a little bit further over, we got right bound and guess. And our answer is down here. This is price. This is revenue. Okay, that's a starting point. So prices must be in dollars. So 7.74 is not an answer. So there's two ways you can get your answer. One is to use tables. So we go table and we scroll down to 7. 7 is 32.20, 8 is 32.80. So our answer is actually $8. And it's here. If you don't like tables, the other way to do this is using trace. And I'll just enter 7. And I get 32.20. This means you have to write it down or memorize this. And then I'll enter 8. And I can see 32.80 is bigger than 32.20. So this is the best rounded price. So number of tickets equals revenue over price. That's 32.80 over 8. And that gives us 410 tickets. Okay, so make sure you answer the question. How many tickets sold? And just so you're clear, I don't think we've covered the definition of a polynomial expression. A polynomial of degree n can be written in the standard form as an, this is a subscript, x to the power of n plus an minus 1, x to the power of n minus 1, and so forth all the way down to a1x plus a0, and this is your constant. N is a whole number, and n all the way down to a0 are integers, and we use this for integers, a fancy z. And the theorems in this chapter apply to polynomials with integer coefficients. Polynomials can have real value coefficients, though, in general. It's just the theorems don't work on the real values. So, examples of polynomials: negative 5 x to the power of 4 plus 2x to the power of 2 plus 3. These are all integers. Everything's good. That's a polynomial. 7x cubed minus 4x squared minus 1. That's a polynomial. These are not polynomials. 3 square root x. Square root x has a power of 1/2. Okay, so that's the same as x to the power of 1/2. So not a polynomial. 4 over x to the power of 2. This is 4x to the power of negative 2. Recall your power laws. Plus 3x cubed. Remember, this needs to be positive or 0. And these are not polynomial expressions strictly because they're not in the right order. This should be 4x cubed plus x plus 3 negative 14x to the power of 4 minus 2x plus 7. And that completes this chapter.